Hello, today we'll discuss about statistical mechanics. So the first question is, what do you mean by statistical mechanics? So statistical mechanics is basically a calculation, a statistical calculation of the substance macroscopic properties or the bulk properties. From where? From the microscopic property of the molecules or the atoms and their interaction. So in simple word, one can say, when you have a bulk material, it consists of large number of constituent particles. They are microscopic particles like electrons and others. Their arrangement and their interactions gives the macroscopic properties. So the microscopic particles gives the idea about the microstates, and the combination of microstates gives you the macrostates, and those macrostates gives rise the macroscopic properties. Now to study the material properties or the macroscopic properties, we should have to learn about statistical mechanics. So there are two types of statistical mechanics. One is classical statistics, another is quantum statistical mechanics. So first we will discuss about classical statistical mechanics, and then we will move for the quantum statistical mechanics. So in simple way, one can say when the particles, that's mean constituent particles or the microscopic particles, are acting like a classical particles, then the statistics will be classical statistics. And when the particles are acting like a quantum particles, they will be considered as quantum statistical mechanics. So first we will discuss about the classical statistical mechanics. This is known as Maxwell-Boltzmann or MB statistics. So what is this Maxwell-Boltzmann statistics? That means in case of Maxwell-Boltzmann statistics, there will be classical particles. They will be known as Boltzons, and they are distinguishable particles. So if you have two classical Boltzons, so they are distinguishable particles. That means they can be named as, say, some as A, and the second one may be considered as B. If you have third one, so you can write this as 3. So they are distinguishable, they are separable particles. Now the idea about the microstates. So here the concept of microstates, that means there will be number of particles arranged in different energy states. How are you going to arrange? So in this case, the arrangement of the particle will be represented as W mb. This is equal to n factorial ni factorial gi to the power ni, where ni is the number of particles and capital N is the total number of particles, and gi is the number of cells or number of states you can think about. So normally for the less number of particles, these values are equal, so one can simply calculate it for g to the power n. So if you have n number of particles and you need to arrange it in different g cells, so then the arrangement will be represented by, for the classical particles, will be represented by this particular equation. Now the next part, the total number of particles in the entire system must be constant. So you cannot take the particles from the system out, then the statistical calculation is not possible. And the total energy of the particle must be constant so that you can calculate the things with this. This particle, the Boltzmann particles, they don't have spin. Actually they are not quantum particles, so they don't have spin over there. They are behaving like a classical particles, which are really following the classical laws like Newton's law and Maxwell's laws, etc. Now the distribution function, this is one of the important thing for the statistical calculation. So when you have a large number of particles, so you need to know what is the distribution function of the system. That's means distribution function means how you are arranging the particles in different energy states. So that what will be the distribution? This is given by this particular relation. So it simply shows 1 divided by e to the power alpha e to the power e ki. So E is the energy for a particular state. Now N and Ni by Gi is known as the occupation index. So how the particles will be occupied in different states is given by this particular relation. So here we have discussed about the Maxwell-Boltzmann statistics, where the particles are classical particles. We know how to arrange the particles, what is the distribution in the system, and they don't have any spin in the system. So what are the examples? So normally when you have a gas molecule at very high temperature and low pressure, so the low pressure means the volume is sufficiently large, but the energy of the particle is quite large, as because the temperature of the particle is very, very high. So they are almost behaving as a classical particles. So in a special case where the system behaves like a classical particles. But normally when you think about a system where we have large number of constituent particles, electrons and alike particles, they are basically quantum particles and they follow quantum mechanical laws. So next, statistical mechanics, the next quantum statistical mechanics, you can say, the next statistical mechanics is given by the quantum statistical mechanics, which was known as the Bose-Einstein statistics, BE statistics. What is this? So here again we need to talk about the particles, the quantum particles, which are following some of the laws. So the first one, the particles will be considered as bosons in the name of Bose, SN Bose. So it's a particles will be considered as boson particles. They are identical, obviously they are identical, and they are indistinguishable. When we are talking about quantum particles, we are talking about a wave function psi, so you really cannot distinguish between different wave functions. Okay, so if you are talking about wave function of electron, their wave function representation will be same everywhere. So you really cannot distinguish those particles. So they are indistinguishable particles. But for classical, they were distinguishable particles. In same way, you can arrange the particles in different states. So this is the relation how we can arrange the particle in different states. So this is Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Again, where N is the number of particles in different states and G is the total number of cell or total number of states in the system. Obviously, the total number of energy and total amount of energy and total number of particles, this is constant for the system. Now, the next important part is as they are quantum particle, they are having some wave function. Now, for the boson particles, they are symmetric wave functions. Okay, they are symmetric wave function, and as symmetric with respect to position. If you exchange the position, the wave function nature will be same. So you can just take an example. If you have some wave function, say psi of r, okay, you are just replaced it by psi of minus of r. Actually, these two wave function will be same. They are, in this case, they will be considered as symmetric wave functions. Now again, when the quantum particles you are talking about, so quantum properties need to be incorporated. So in this case, the wave function having some spin. So which type of spins are there for the boson particles? Either this will be 0 or integral spin. So this is denoted as 0 h cross, 1 h cross, etc. Now the distribution function of the system, this is given as 1 by e to the power alpha e to the power ei kt minus of 1. Now examples, there will be photon, phonons, helium-4, all muons are the examples of boson particles. Now the next one, you have another quantum statistical mechanics. This is known as Fermi-Dirac or FD statistics. So in case of Fermi-Dirac statistics, again particles are quantum mechanical particles. They will be considered as fermions. Again, they are indistinguishable. They are wave function. They are indistinguishable particles. Obviously, the total energy and total number of particles will be fixed, and they are quantum particles. So there will be some spin, and this spin will be considered as half spin. And as you have mentioned, this is quantum particles. So obviously, we need to think about the quantum wave functions. So the quantum wave functions, that's mean if you are representing any function, any fermions by f of r, now this wave function will be antisymmetric in nature. That's mean antisymmetric means, so if you are considering wave function the same wave function at minus of r. Obviously these two will not be same in case of fermions, but in case of bosons this will be same. Now this relation, this particular relation, the concept of wave function in an antisymmetric form, this gives the idea about the Pauli's exclusion principle. So as these wave functions are not symmetric in nature, they are antisymmetric, so this must be following Pauli's exclusion principle. And what is that Pauli's exclusion principle? We all know that 4 quantum number must not be same. If you are writing wave function in that fashion, so then the Pauli's exclusion principle will be validated over there. Now how we are arranging the particles? This is gi factorial n factorial divided by n factorial g minus n factorial, where n is the number of particles in different microstates and g is the number of microstates or number of cells. And again the distribution function is given as, the nature of the distribution function is e to the power alpha e to the power ei by kt at certain energy ei and plus of 1. Okay, so e alpha is denoted as minus of ef. This is known as Fermi level energy. The examples of fermions, these are electrons, protons, neutrons, helium-3 and all hyperons are the fermions. So today we have discussed about the basic idea about statistical mechanics and the different types of statistics. So in simple way we can say that statistical mechanics is the study of a macroscopic properties by the help of microscopic particle arrangement and interaction. And how the particles will be arranged and how the particle will be interacted, they will be defined by 2 different types of statistical concept. One will be considered as a classical concept, classical statistics, which will be known as the Boltzons. There will be another 2 types of quantum statistics. So the quantum particles will be considered, they will be considered as bosons and fermions. So the boson and fermions arrangement we know about the distribution function. Remember it, in case of Bose-Einstein distribution, this is minus of 1, whereas in Fermi-Dirac statistics this is plus of 1. Remember it, in case of boson, the fermion, in case of boson the wave functions are symmetric in nature, whereas in case of fermion they are antisymmetric in nature. In case of fermion it is following Pauli's exclusion principle, as the wave functions are antisymmetric, but in boson they are not following Pauli's exclusion principle. That means they are symmetric wave functions. So we can put any number of particles in any number of states. Thank you.